Welcome back, Focus Learners, to another deep dive on the Explainer. Today, we're grabbing our mathematical magnifying glasses and, well, we're decoding the language of the universe, algebra. Look, if you've ever stared at a math problem where numbers are suddenly mixed up with letters and just felt totally intimidated, don't worry, I've got you. We're going to go through a really clear step-by-step breakdown of algebraic expressions. By the end of this, you're going to see exactly how this whole mathematical scaffolding is built. So let's start with a little mystery. If I hand you a closed jar of sweets, how on earth do you mathematically represent what's inside? I mean, you can't see them, you definitely haven't counted them, but you know they're in there, right? This real-world mystery is actually the ultimate hook for our topic today, because algebra gives us this brilliant, super simple toolkit to represent the unknown. Here's our quick roadmap for today. First, we'll decode variables and expressions. Second, we'll look at the anatomy of algebra. Third, sorting like and unlike terms. Fourth, adding and subtracting those expressions. And finally, multiplying and dividing algebra. Let's get right into it. All right, Section 1, decoding variables and expressions. So, what exactly is a variable? Well, it's simply a letter or a symbol used to represent a value that can change. The absolutely crucial thing to remember here is that in algebra, letters aren't just letters. I want you to think of them like containers. They're basically empty boxes holding unknown numbers, and when we combine regular numbers with these variable containers using math operations, but without an equal sign, we create what's called an algebraic expression. Okay, let's bring back our jar of sweets and see how this actually plays out. Step 1, we have no idea how many sweets are in that jar, right? So we just call that unknown amount n. Our expression is literally just n. Now, check out step 2. If someone hands you 6 more sweets, your expression becomes n plus 6. Simple. In step 3, let's say you get hungry and eat one sweet from your original jar. You represent that physical action as n minus 1. And finally, step 4. If you're lucky enough to score 3 full, identical jars, you don't write out n plus n plus n. That takes too long. You just write 3n. See how beautifully the math just perfectly reflects our physical reality? So how does this map onto real-world values? Well, variables basically come in 2 flavors, fixed and varied. A fixed value is an unknown that just doesn't change. Like, say, K represents a bank's annual fixed deposit interest rate. You might not know what it is off the top of your head, but it stays constant all year long. On the flip side, we have varied values. Imagine T represents the travel time from your house to school. Now that value fluctuates every single day, right? It depends on traffic, the weather, whatever. The container, the letter T, is the exact same, but the actual number inside it changes. Now let's try combining different variables. Walk through this classic shopping trip with me. In step 1, you buy 5 apples. You don't know the exact price, just that they are X cents each. So your cost is 5X. Step 2, you buy 8 oranges. These cost a completely different unknown amount. Let's call it Y cents each. That cost is 8Y. In step 3, we want the total. You literally just add them together. So your expression for the total payment is just 5X plus 8Y. But wait, what happens when the mystery is finally solved? Like, what if we suddenly discover the secret values hiding inside our variables? Well, we just substitute them right into the expression. Let's look at this one. 8X minus 5Y plus 7. If someone tells us, hey, X equals 3 and Y equals 2, we just pop those numbers straight into our containers. It becomes 8 times 3 minus 5 times 2 plus 7, which turns into 24 minus 10 plus 7, giving us a final answer of 21. It's like unlocking a puzzle. Okay, moving on. Just like in biology, mathematical expressions have a very distinct anatomy that we need to dissect. Section 2, the anatomy of algebra. Now pay close attention, because these next 2 definitions are absolutely vital for everything we do next. A term is either a number or a variable in an expression. It's the whole chunk. A coefficient, on the other hand, is any number or symbol multiplied by the variable within that term. To put it simply, the term is the whole entire piece, and the coefficient is just the multiplier attached to the specific variable you're looking at. What's really fascinating about coefficients is how totally flexible they can be, depending entirely on your perspective. Look at this huge term on the left, -3 k squared mn. If we decide our variable is k squared mn, then the coefficient, the part multiplying it, is just -3. But look at the second row. For that exact same term, if we just isolate mn as our variable, the coefficient actually becomes negative 3k squared. And if the variable we care about is 3k squared, well, then the coefficient is negative mn. Literally isolating a different part of the exact same term completely changes what we call the coefficient. Pretty cool, right? All right, anatomy lesson complete. Now we need to organize all our pieces. Section 3, sorting like and unlike terms. Check out the visual boundaries separating our terms here. On the top, we have our like terms. These are terms where the variables and their exponents are exactly the same. So 7x and negative 4x are like terms. Even 3abc and 0.5 bca are like terms because the letters themselves are identical, even if the order got shuffled a bit. Now below that line, we have unlike terms. This happens when the variables, or the exponents, are different. For example, 2x and 2x squared, no way, you cannot group those together. That exponent completely changes the container. Similarly, 2x and 2y are also unlike terms, apples and oranges. So now that everything is sorted, we are finally ready to put these terms through the machinery of basic arithmetic. Section 4, adding and subtracting expressions. Let's simplify this long expression together, 3x plus 5y plus 8x minus y minus 9. Now you can't just mash this all together into one giant blob. Step 1 is the necessary bridge. You absolutely must gather your like terms first. So we group the x's together. That's 3x plus 8x. Then we group the y's together, 5y minus y. And that lone number, the minus 9, it just stays by itself at the end. In step 2, we just add or subtract those specific groups. 3x plus 8x is 11x. 5y minus y is 4y, leaving us with a beautifully simplified answer of 11x plus 4y minus 9. So satisfying. Okay, last stretch. The rules change just a tiny bit here, but the underlying logic remains incredibly elegant. Section 5, multiplying and dividing algebra. First up, let's look at repeated multiplication. Just like with regular numbers, if you take an algebraic term and multiply it by itself repeatedly, you create a power. So m times m times m times m simply becomes m to the power of 4. And you know what? This works for whole expressions too. If you have the group, in parentheses, x plus 7, and you multiply it by the identical group, x plus 7, it simply becomes x plus 7 all squared. Now let's try multiplying different terms together. Take a look at this example. 3ab squared times 4a cubed b. The real secret here is to understand the logical why behind it. If you look at step 1, we just expand it all out. By expanding it, we can easily see exactly how these variables stack up. In step 2, we gather the regular numbers with the numbers, the a's with the a's, and the b's with the b's. Then in step 3, we just do the math. 3 times 4 is 12. A times a cubed is a to the power of 4, and b squared times b is b cubed. So our final simplified answer is 12a to the power of 4 b cubed. And this brilliantly illustrates our final concept today, division, because we use the exact same expansion logic. Say we want to simplify 20m to the 4th n squared divided by 5m squared n cubed. Step 1, write it out as one big expanded fraction. Step 2, just eliminate the common factors on the top and the bottom. You literally just cross out the matching m's and n's. And what are you left with? Well, on top, 20 divided by 5 is 4, and you have 2 m's left over, so that's 4m squared. On the bottom, you just have one n left, making our final quotient 4m squared over n. Breaking it down like this makes canceling out common factors incredibly simple, right? Wow, okay, we've covered a lot of ground today, moving all the way from mysterious jars of sweets to canceling out complex exponents. So I want to leave you with this one question to think about. Now that you know letters are really just containers for numbers, how could you use a variable to calculate an unknown value in your own daily routine tomorrow? Maybe it's the fluctuating time of your bus ride or, budgeting for your snacks. The truth is, algebra is literally everywhere once you know how to look for it. Thank you so much for joining me on this explainer. Keep asking questions, keep organizing those variables, and I will see you next time.